Now for one of the last topics of acids and bases, yes, you can say, phew, sigh of relief, acid-base titrations. Okay, how could we forget titrations? So first of all, let's look at some of the keywords that we talk about in acid-base titrations. First of all, titration itself. Titration itself is the addition of a solution of a known concentration to a solution of an unknown concentration until you get to the end point. So a titration could really be for anything, okay? And you have done titrations of acid base, of redox, you can have precipitation titrations, anything is possible. In case of the acid-base titration, you're working on acids and bases, which means that we can also draw a pH curve, which you will see later on is actually a little bit of a useful technique to do. So that's basically what a titration is. Then a standard solution is a solution with the known concentration, because you have to have at least one that you know the concentration of. Titrant is a solution that is placed in the burette. The unknown then is placed in the Erlenmeyer flask. You can have it the other way also, okay? It doesn't matter. The titrant is in the burette. Whether you know the concentration of the one in the burette or the flask, it doesn't matter. Equivalence point is when there is a stoichiometric equivalence of acid and base that has been added, and the equivalence point has to do with the mole ratios. Okay, so whether it's 1-to-1 ratio, 2-to-1 ratio, that is going to be the equivalence point. The end point of any kind of a titration is when the titration is finished, and this is usually given by the help of the indicator. Okay, so the endpoint may not necessarily be the equivalence point, okay, because equivalence point is based on stoichiometry, and equivalence point technically should be a pH of 7, okay, which means that everything is completely neutralized. On the other hand, endpoints sometimes, since they're based on indicator, they may not be exactly 7, but they indicate that all the acid and all the base has reacted, okay? But the thing is that we know already that some acids and some bases are weak acid bases, which means they form conjugate acid and bases, which means that the pH may not be 7, okay? So indicator is a really good way of telling what the endpoint is going to be. And in some cases, that is also equal to equivalent point, not all the time. Indicator is, of course, then the chemical which changes the color at the end point, and in some cases, equivalence point also, depending on what kind of a titration you're doing. So the choice of the indicator depends entirely on the acid base that you're dealing with. So unless you really know what kind of an acid base you're working with, you may not be able to figure out what indicator you can use. Now we have a whole bunch of indicators that you can use and then determine which acid base is good for which indicator, or which indicator is good for which titration. Okay, so indicator has to be chosen carefully. So what kind of acid-base titrations do we have? We have 3 different kinds. You have the strong acid and a strong base titration. For example, HCl and NaOH. That will give us NaCl and H2O. And remember, if you have a straight arrow, boom, we're going right to the front. Okay, and so there is nothing going back, which means that the final products are going to be neutral, because remember, strong acids, strong bases give us neutral salts. So this is the only place where your equivalent point and your end point is going to be the same. Okay, strong acid, strong base, this is it. So which means that adding even 1 drop of a titrant will completely change the pH. Okay, drastically it will change the pH, because everything dissociates. Okay, so even if you have 1 drop more, suddenly the pH shoots up or down. Okay, wherever. So we have to be careful when we're doing strong acid, strong base titrations. Weak acid and a strong base. If you have a weak acid and a strong base, it means that the final product is going to be a conjugate base. If it's a conjugate base salt, then your pH is going to be slightly more than 7, okay, which means it's a basic product that you're getting. Strong acid and a weak base. Weak bases give acidic salts. So when you have an acidic salt, the pH is going to be less than 7. What does that mean for us? Okay, that means that the equivalence point and the end point are not going to be the same, okay, for us, because pH is not 0 for weak acid and weak base titrations. All right, the equivalence point and end point is the same for strong acid, strong base, but not for these two. And we have to do titrations for all, so we have to understand what's going on. So let's look at an example of a strong acid-base titration. Now you've done this in GenChem 1 also, so it might be just a little bit of a review as well, but anyhow. Calculate the pOH and the pH of a solution in which you have 10 milliliters of 0.1 molar HCl, and that is added to 25 milliliters of 0.1 molar sodium hydroxide. Okay, so which means that you have a strong acid and a strong base titration going on over here. So let's see what happens. What you will do is calculate the moles of sodium hydroxide and the hydrochloric acid and see whichever one is higher and then subtract the two. You will then add the volume of both, which is 10 plus 25, and that is 35 milliliters, and then you will determine the concentration, and then you will determine the pH. So it's kind of like a 4-step process. Okay, so let's take it step by step. The overall reaction is this, which you need. Okay, please don't forget, when you're doing titrations for acids and bases, you need the reaction because you need to figure out the mole ratio. If your mole ratio is not correct, then your moles will be wrong over here. Okay, if your moles are wrong, everything else is going to be wrong. So please make sure you write the acid-base equation and then see if the mole ratio is 1:1. So moles of HCl that we are adding is 0.1 molar times, and then of course the 10 times 10 to the negative 3, we have to convert this into liters from milliliters. So we get this much moles. The moles of sodium hydroxide, same thing, and you have 0.1 moles, and now you have 25 milliliters. Okay, just by looking at this, you can probably tell that you have more of sodium hydroxide because both of the concentrations are the same, right? 0.1 molar, 0.1 molar, and you have 25 milliliters of sodium hydroxide. So you obviously have excess of the hydroxide ions in there. So here's the moles of sodium hydroxide in there. So which means that all of your hydrochloric acid has reacted. If it's all reacted, then of course there is hardly any hydronium ion. It doesn't mean you cannot calculate the pH. You can still do that, right? But anyhow, let's go forward. So all of the HCl reacts, which means that you're subtracting 2.5 minus 1.00 times 10 to the negative 3 moles. So subtract the lower from the higher, and the sodium hydroxide is in excess. Okay, so that's what's remaining. Now what you will do is add the volumes up, which is 35 milliliter, which is equivalent to 0.035 liters. Now you will calculate the molarity of the solution. So the molarity of the solution is whatever moles is left over, which is the sodium hydroxide here, divided by the volume, the new volume, not the old one, the new volume, and that gives you the molarity. So now this is the hydroxide ion concentration over here. Okay, and so what you will do is you will use the pH equation to figure out what the what the pH is, okay, of this solution. So you can calculate first the pOH using 4.29 times 10 to the negative 2, which turns out to be 1.368. Okay, that is the pOH, and then you calculate the pH of the solution, which is 14 minus the 1.368, and that gives you the pH of the solution, very high, and that's pretty normal. And you can see it's just a little bit of excess of sodium hydroxide, but the pH is so high for this. Okay, so let's see in a calculation for weak acid and a strong base titration. So the question is, what is the hydroxide ion concentration and the pH at equivalence point in the titration of a 500 milliliter 0.100 molar propionic acid HPR and 0.050 molar calcium hydroxide? And Ka is given to us, which is going to be for propionic acid because that's the weak acid that we're dealing with. A few things here before we go on to look at the solution of this is we're calculating the hydroxide ion concentration, okay? And this should kind of trigger in your mind, why am I looking at hydroxide? And that's because you're dealing with a weak acid. So a weak acid will give you a stronger conjugate base, which means that you will have hydroxide ion concentration in your final product. The other thing is here is that you're dealing with equivalence point here. When you're dealing with equivalence point, you have a mole ratio that is equal, okay, of the acid and the base. The third point to note over here is that you don't have the volume of calcium hydroxide, okay. You have the volume of the propionic acid, but you don't have the volume of calcium hydroxide. And lastly, the fourth point over here to note is the structure of propionic acid is not given to us. And honestly, it doesn't matter because all we need to know is how many protons are needed. Okay, because for the mole ratio, you need to know whether you have a monoprotic, diprotic, what sort of protic acid you have. Okay, so we have a monoprotic acid. We will need to write equations. Okay, and remember, we always have to write equation for acid-base titrations just so that we know that our mole ratio is 1:1. So let's look at the solution now. There are going to be 4 parts to this problem, 4 or 5, depending on how you view this. First of all, we're going to calculate the moles of propionic acid, okay? And propionic acid, we can do that because we have the volume and molarity given to us. So we're going to calculate the moles of propionic acid. Then we're going to find the volume of calcium hydroxide needed. And how we're going to find the volume of calcium hydroxide is when we know the moles of propionic acid, then we know the moles of calcium hydroxide. And we have the molarity of calcium hydroxide. So we're going to use all of that information to find the volume of calcium hydroxide. And we can do this because we're dealing with equivalence point in which the mole ratio is equal. Once we have the volume of calcium hydroxide, we will find the new volume, which is going to be 500 plus whatever we calculate, and then we're going to use the equilibrium method to find the pH, okay, which is the ICE method, because this is a weak acid base titration, weak acid strong base titration. So then we're going to use the equilibrium method. All right, so let's get started. The first thing, calculate the moles of propionic acid, not hard to do. Piece of cake, molarity times the liters will give us the moles of propionic acid, which is 0.05 moles. Then you write the equation, and again, I stress you have to write the equation so you get the mole ratio. Unless you know already looking at the structures here that the mole ratio is 1:1, then it's fine, but otherwise I would highly recommend that you write the equation out. So here, once you write this out, you know that calcium hydroxide is giving 2 hydroxides. So you need 2 moles of the propionic acid, okay, to neutralize that. So here is our calculation, and this is just showing you the mole ratio. So moles of calcium hydroxide needed are the 0.05 moles of HPR, and then of course the mole ratio, 1 mole of calcium hydroxide to 2 moles of propionic acid, and that gives us 0.025 moles of calcium hydroxide. Once we know the moles of calcium hydroxide that we need, now we can calculate the volume using the molarity. So moles divided by molarity will give us the volume, which is then 0.5 liters. It just happens to be the same as what was given to us for propionic acid, but it may not be the same. So don't get fooled by that, okay? Just because it's the same volume, it just happens to be because of the concentration of calcium hydroxide. It is half of that of propionic acid, so you need twice of this, okay? So anyhow, once we have the new volume once we have the volume for calcium hydroxide, we're going to find the total new volume that we have, which is 500 plus 500 to give us 1 liter. Very, very convenient for calculations. So we have 1 liter of new volume. The moles of the propionate ions, and this is the important part because this is what we're going to carry ahead for the pH and the hydroxide ion concentration, because at equivalence point, technically you have gotten rid of all the hydrogen ions and all the hydroxide ions. So what is remaining now is going to be the propionate ions. So how do you know how many propionate ions you have? Well, that is the concentration that you started with, okay, for propionic acid. So 0.05 molar of propionic acid, so which means you still have 0.05 moles of propionate ions that are left in there. And then you find the concentration of the propionate ions, because that's what you need to carry on with your calculations for the ICE method. And so 0.05 moles divided by the 1 liter gives you 0.05 molar concentration of the propionate ion. So in the next slide then we have to do the ICE method, where we're going to use the propionate ions. This is the concentration that we will use, okay, for the propionate ions. Okay, so now for the ICE method, okay, over here. So carrying on from the previous slide where we calculated the concentration of the propionate ion. And so now this is going to be our reaction since we are setting up for the ICE method. So propionate ions, which was formed from the propionic acid, this is the conjugate base for it. So remember at equivalence point, we don't have any hydrogen ions or any hydroxide ions left. We only have water now. So the propionate ions will react with water to give propionic acid and then the hydroxide ions over here. So you're starting with propionate ions. That's the calculation we did in the previous slide. So 0.05 molar was the concentration for propionate. And then we have 0 and 0 for propionic acid and hydroxide. Remember the question asked for hydroxide ion concentration and then also the pH, okay, for the solution. So that's what we have to do. So then the ICE method, which is then a change, is minus X and plus X's, and then of course equilibrium concentration where we have the 0.05 minus X and then X and X. Now since we are dealing with hydroxide ion over here and propionate over here, we're going to have to deal with Kb, not Ka. If we were dealing with hydronium ion concentration here, then we would deal with Ka, okay? But we were given Ka of the propionic acid, so we will just go ahead and calculate the Kb for it. This is something you have to keep in mind when you do these calculations, okay? Is don't just right away use the Ka. Calculate the Kb if you're using the hydroxide, if you're calculating for the hydroxide ion concentration. So Kb is Kw over Ka, and that gives us 7.7 times 10 to the negative 10. Simple calculation, but it's just something that you have to keep in mind, okay, to do. And then you go ahead and set up your equilibrium constant, the Kb, which is very simple. We've done this a zillion times before. So products over reactants. And then Kb is 7.7, which we just calculated. X squared over 0.05 minus X, which is the propionate ion concentration remaining. And again, we're going to go ahead and ignore X because it makes our life easy. No, because it's very small. Okay, so we'll go ahead and ignore that. And then you calculate for X, okay, from X squared. So all of these wonderful calculations, and then X turns out to be 6.20 times 10 to the negative 6. X is hydroxide ion concentration. So that's what we just found out. That is part of our result. And then the next part to do is to calculate the pH of this. So you'll go ahead and calculate the pOH for this. pOH is 5.21, which you will take the log of this, negative log of the concentration here. And once you know the pOH, which is 5.21, you'll calculate the pH, which is then 8.79. So again, it just proves to us that even though you have equivalence point, which means that you have neutralized all the hydrogen ions and the hydroxide ions using the acid base, the propionate ions, okay, are still producing some of the hydroxide ions, and so it increases your pH by a point of 1.79, okay, so from neutral. So equivalence point, remember, it's only for the acid base, it's not for the salt. Okay, that's the end of this problem. Yeah, it's a little bit longer to do for weak acids and weak bases titration, but you know, for strong acids, strong base, a lot easier. Here are some titration graphs that are kind of important, and I usually do ask these questions in the exam as to which graph belongs to which kind of a titration. Okay, so for example, if you have a strong acid and a strong base titration, all right, this is what the titration curve is going to look like. So you have low pH, which means that you're starting with the acidic pH or the acid and you're adding base to it. And then as soon as the equivalence point is reached over here, the end point is reached over here, boom, suddenly one drop will change the pH so much. It can take it from 5 to 11 in one drop. Okay, the middle of that curve is what we call the equivalence point, and that is going to be 7 for a strong acid and a strong base. And usually the equivalence point is also the end point, which means that's where the color will change, okay, for strong acid, strong base titration. Okay, so now in this case where you have a strong base that is being added to a weak acid, how do you know that we're adding this to a weak acid, and that's because you're starting with a low pH. Okay, and it also tells you you're adding sodium hydroxide. Okay, so read the chart carefully. So you're starting from a weak acid over here, which has a pH of 3, and then you keep adding sodium hydroxide, and at one point then you reach the end point. Okay, and usually the way you tell that you have an end point is that your graph is pretty much straight, okay, as a line like this, okay, which means that you can the pH will change, okay, at that point. Now in this case, if you take the middle of this line, the straight line here, and you project it out here, you can see that the equivalence point is not at 7. Okay, it's a little bit above 8 because you're adding to a weak acid. Weak acids give conjugate bases, and therefore the pH is actually a little bit higher, okay, over here than 7. Okay, and then if you add strong acid to a weak base, okay, so now you're adding acid, which means that you're starting with a higher pH over here. So this is the base, and if you take the base and you keep adding the acid, adding acid, and suddenly you reach the end point. And if you take the straight line over here and take the midpoint of it, and you will see that it's again not at 7. It's going to be lower than 7 because you have a weak base, and a weak base will give, yes, strong conjugate acid. Okay, and so therefore your pH is going to be lower than 7. Okay, so the graphs for strong acid base and all of these titrations, they differ. Okay, and so you should be able to recognize looking at the titration curves as to which graph belongs to which titration. Indicators. Usually I don't ask much questions about indicators, but just so that you know that you can have different indicators and different pH ranges for that. And the nice thing about indicators is that, of course, the colors are beautiful. Okay, and the colors change. And so you can select your indicator according to the pH range of the indicator. Okay, and the pH range of the titration that you're working with. The titration curves that you saw in the previous slide, the straight line, that is what you're looking at. Okay, that's your pH range that you should be looking at, all right, for your titration to find a good indicator. The one below over here, or the picture that is shown to you, is actually of a cabbage juice indicator. And cabbage juice, this is the purple cabbage, okay, and take out the juice of that, which means if you boil it, the purple color that you get is a really nice indicator. And it changes colors with different pH levels. Okay, over here, this is the basic one and this is the acidic one. Okay, so strong bases will give you greens and yellows, and then strong acids will give you pinks and purples. Here are some examples of indicators and what color you would see in the acid and what color you would see in the base, and here's the pH range. Okay, so for example, if you want to use methyl red, then the color changes for it is going to be 4.2 to 6.3. So obviously you're not going to use it for a weak base, a weak acid titration, because a weak acid will give you strong conjugate base. So your pH is going to be higher. So you really don't want to use the methyl red for that. Okay, and so you choose your indicator depending on the pH range of that indicator. You have used phenolphthalein before, okay, and phenolphthalein gives you a nice range of 8.3 to 10. It's a nice strong base. So really, in conclusion, you need to know how to carry out the titration calculations, which means to calculate the pH of strong acid and base titrations, which are fairly easy to do, but just remember to write the equation and do the mole ratio. Okay, so don't forget the mole ratio when you do the calculations here. Find the total volume and then calculate the new molarities. Don't forget to subtract also, okay, from higher concentration to lower concentration. And then you should be able to calculate the pH of a strong acid versus a weak acid base titration. And what this is, of course, you calculate the moles, you calculate the volume again, and then you have to use the ICE method, okay, for this one. One point I would like to mention, which I have not mentioned over the entire slides, is that you will hardly ever get any titration for a weak acid and a weak base, because for a weak acid and a weak base, you really cannot get to an end point or to an equivalence point, because you are creating a conjugate acid and a conjugate base, which then keep creating an acidic and basic situation. And so you will never see a weak acid, weak base titration, okay? Only for strong acid or strong base plus weak acid base titration. Then you should be able to look at the graphs and be able to identify what kind of graph it is, whether it is a weak acid base titration with a strong acid base, etc., etc.